Okay. So we're going to apply Faraday's law to a very strange sort of narrow scenario that is very classic physics problem. So if you're wondering what the applications are, there's indirect applications, but these problems are like uber simplified to make them nice and pretty physics problems. So we're imagining taking a square loop of wire and pulling it outside of a B field. So for the cross-sectional area of that wire, as we pull it out, there's less and less B field lines going through it. So there's going to be an induced current, an induced B field, and an induced EMF. So if the B field is decreasing, the external B field is decreasing in that loop, what's the direction of the induced B field? Chris says into the board. Anyone else?
Okay, it starts going in and then it changes to in this direction, going out direction. So the induced field is still going in.
Well, there's, I'm not sure that your explanation gives me a lot of confidence there, but there is an external B field that's constantly pointing into the board. The external B field doesn't change. The only thing that's changing is that we're pulling our loop out of that B field. So as far as the loop is concerned, the B field is decreasing. Okay, so if yes, Chris also says it's into the board. If it's decreasing, our induced B field is going to be into the board to oppose the decrease. So if our induced B field is into the board, what's the direction of our induced current? Clockwise? Clockwise, clockwise. Yes, this is another one where we want to be really careful that we use the direction of the induced B field to find our current direction, because it's not drawn. We have to draw that ourselves and then figure out the current direction from our drawn induced B field. Okay, so since it's a square loop, we've got these 4 sections of straight wires, and we've got now current running through that loop. And if it's in a B field, then we've got forces acting on each of those sections of wires. And so this can be doubly confusing, because when we use our right-hand rule, the B field is now the external B field. So for this section of wire, our current, we said, was clockwise, so the current's this way. The external B field's into the board, so the force is down. You can follow your hand around, and the force is to the left on the left side, the force is up on the top, and the force is to the right on the right-hand side. Of course, I should actually say there's actually no magnetic force on the right-hand side, because this part of the wire is no longer in the B field. So there's no magnetic force, but you do have a force on that side, and that's your pulling of the wire. Yeah, Chris?
So for our right-hand rule to determine the force that's acting on the wire, is the reason that we use the external B field sort of similar to the reason you can't push yourself in space, like you can't be acted on force that's created by your own magnetic field.
Yeah, that's a good way of putting it, right? So there's got to be that external force, or the external B field is creating that external force. I think this may be one that would help to do color coding on. Just this one isn't too bad because the external B field and the induced B field are in the same direction. So maybe I'll do the reverse case where I'm trying to push this wire into the field. So if I'm applying a force this direction now, then I've got external B field lines increasing in my loop. So what's the direction of the induced B field?
Coming out.
Coming out, yeah, out of the board. So that's our induced B field. And the induced B field coming out of the board, what direction of current do we get from that induced B field? Counterclockwise. Okay, and then to color code this, our right-hand rule is using the blue B field to figure out the direction of the force. So on this section of wire, the current is down, the B field is into the board, so my force on that section of wire would be to the right. And as I follow my current around, the force on this section of wire would be up. Up here would be down. And then again, we wouldn't have any force on that side because it's not in the external B field. Yeah, Nolan?
So basically what that means is that the forces resist the applied force. So you try to push something into a magnetic field, it will resist.
Yeah, and it will resist in equal measure to your push. So the sum of forces in both directions is 0. The y direction, it's pretty obvious. These two forces are going to be equal and opposite. If I call this 1 and this one 3, FB1 minus FB3, they're equal and opposite, so they cancel. But as you increase your force on this side, this force is going to get bigger. So those ones are always in opposition as well. So FB2 minus F applied are always equal and opposite. So you can make this relationship now where they are equal. And then I really someday want to get like a big horseshoe magnet. When I was TAing at Oregon State, we had a bunch of these and we did this eddy current lab. And this is the same idea. You've got this big magnetic field and then you take this plate, aluminum plate on a stick, and you just swing it through the horseshoe magnet, and as soon as it hit the magnetic field, it was like trying to push it through quicksand. It was like, ugh, and then, ugh. But as soon as it was out of the field, it was fine. And this is the same idea. If you've got a plate, you create these eddy currents. Those eddy currents are the induced currents that are opposing the increasing B field as you're trying to push it into the B field. And so you get a very strong force opposing your applied force. So what this means is as you're pushing it, there's no acceleration, so this is going to move at a constant velocity. So whether you're pushing or pulling, you're always going to have a constant velocity. So we can solve for things, now that we understand the physics behind this, we can solve for the induced current in the loop. So if we first look at the induced EMF equation, we said that was d flux over dt, and if we do the simplified flux of B times A, the B field is constant, that's just some external B field. Like my example, that could be from a horseshoe magnet, so it's a constant external B field. But the area is changing. You're only interested in the part of the loop that actually is inside the B field. And in this case where you're pulling it out, that area is shrinking. And so I drew an X to denote the portion of that loop that's actually in the B field. And you could solve for the area as L times X. And so the X part of that is changing. That's going to be affected by your pull. So if I throw in for area L times X, I put that in here, the B field is constant, the height of your loop, L, is constant, so the only thing affected by time would be your x term, dx dt. And what's dx dt? Velocity. So now we've got an equation for induced EMF that's related to the velocity, BL times V. And using my little picture here, I'll show again that the L is the height of that loop. Okay, and once we have induced EMF, we can throw that into Ohm's law, V equals IR, arrange that for current, and you've got EMF over resistance. And so where does the resistance come from? There's going to be a little bit of resistance in any kind of wire. Sometimes for these problems, they'll actually throw a resistor in series in this wire, and then you'll actually have some kind of resistor value that isn't just the little bit of resistance in a wire. And then if we want to know what applied force you're going to be using as you're trying to pull this out of the magnetic field, we can throw that force into our equation from last week for the magnetic field. So our applied force, we said, was equal to the magnetic force on this side of the loop. And the magnetic force on this side of the loop we can get from the cross product, I, L cross B. And we can write out the cross product is ILB sine theta. The angle in this case is the angle between the B field and our current. So what's the angle between the B field and the current? 90? Okay, so the sine 90 goes to 1. And so we have ILB as the solution to that force equation, and we just solved for I, BLV over R, so we can throw that in here. And so we end up with B squared L squared times V over R. So that would give you how much force you're applying to your loop. And then taking it one step further, we remember about power. Power was force dotted with velocity. If your force is in the same direction as your velocity, then the dot product just becomes a multiplication. So you're just doing the applied force times velocity. And then that makes everything in the numerator squared, divided by the radius, or the resistance. And so that would give you power as well. So it's kind of cool. I mean, you can solve for all these things, but again, there's not a whole lot of engineering applications. This is just a sort of very physicsy kind of problem. Oh, they also like to ask you, like, what's the rate of, what do they say, when they're trying to trick you into asking something that doesn't sound like power but actually is power? Like what's the rate of energy dissipated by the resistors? They say that. What they're asking for is the amount of power burned up by the resistors. So our power equation related to resistors